Okay, I want to start with a better answer to a request. I don't think I justify the answer quite well. So the request was for solutions for PAT to provide binaries rather than just the handout. Well, I'd love to do it, but I cannot do it for two reasons. One of them is that there are no such thing as a binaries for Python, because there is bytecode, but you can reverse engineer it in a few minutes. So that would leak the solution out, and the project took quite a while to prepare, and we cannot change it every year, so it must not leak out, hence you are getting only hard copies. And there is an educational benefit to getting just the hard copy, and it is that you actually need to read what the solution is. Well, you could just retype it, but I don't think it will work that way. So that's how it is. I'm sorry. Yes? You could, but then you couldn't test it on your own machine, right? Because you would need to always go through the autograder. The binaries would need to reside on the server, so you would need to somehow check in. It would need to be shipped to the server. And so that's something I will insist on. I'm sorry. If you did not finish the assignment, we expect you at the very least to understand what the right solution is and fix the few bugs by taking the hard copy of the solution and putting them in.
Can we find out what test cases we missed on PA1?
Test cases on PA1, we are going to release pushed into your repositories, the test cases. Not all of them, but I think the strategy that we'll use that we'll push back 5 test cases for everybody based on which are the most frequent ones that people failed. So if you failed 10 test cases, you'll get 5 back, those that caused most problems for everybody.
So if we type in the handed number, they're not going to work right out of the box. Is that what you're saying?
I think they should. Yeah. Well, I don't know now. Okay. That was probably a problem. The question was, what do we do? Can you ask for a resubmit after you picked up the I see. Oh, you still can pick them up, right? Absolutely. So you can just come to the office hours tomorrow and pick them up. Yeah, there is a stag on Sean's and Thibault's desk, and you can pick them up. Excuse me? I don't know if they are going to be there. Probably not. I don't think either of them has office hours after class. But tomorrow you can pick them up. Okay, so today I just want to say that we are going to give extra credit for any bugs that you find in the handout, solutions, starter kits, and we'll keep track of it on Piazza. Today, Thursday is no laptop days, and that's good because there is a lot of material that we want to cover that you may want to think about every slide that we'll go about. So parsing, why do we care about parsing? We want to make sense out of these sentences. Sentence like this one. You see a problem that shows up in parsing of the sentence. So depending on whether there is a serial comma or not, depending on whether you put a comma or not, the association of Mother Teresa and Pope could be, well, they could be my parents. That was the meaning as written because there was no comma. Or they could be the people to whom this lecture is dedicated. And you can guess the meaning from the context, but without the comma, indeed, the meaning was that they are my parents. And the second one is here, and again, there is an error. There is a hyphen which changes the meaning to, instead of 7 doctors, these are doctors who are 7 feet tall or wide, or I don't know. That's one of the two. And then a meaning of this, which is more relevant to the class. Can you see what the ambiguity might be here? Right. So to put it more concisely, the answer is good, but to say we are really asking, is this else associated with this if or with that if, right? It could be one or the other. And so in general, parsing is the process of taking text and turning it into some sort of structure, usually a tree that shows how things are associated, how they are evaluated. It's true for natural language. It's true for computer programs. And there is a lot of text out there. Just think of HTML, JSON, and all the things that you will need to parse, in addition to programs. So grammars are the things that describe strings. Essentially, a grammar is what the description of a set of strings. That set of strings that the grammar describes is a language. And we have seen it before. But let's recap it on the case of regular expressions. So regular expressions are described with a grammar that is inductive, recursive, almost like any other grammar. And what it says that there is a base case, and any character C is a regular expression. So A is a regular expression, and so is B, and so is C, and so on. And then the inductive case, if we find regular expressions E1 and E2, then the alternation, the concatenation, clean closure, and the regular expression in parentheses, these are regular expressions as well. So the grammar therefore describes which strings are sort of legal strings, legal program strings that we want, and indirectly describes which are not. Okay? So give me a few examples from the language. Just one quick example that is derivable with this grammar. A will work. Okay. One more. Okay, so we'll do this. This is from the language, clearly. Give me a few that are not from this language. So a dot. Well, now it really depends whether dot has a special meaning or not. According to our description, the dot would be probably just a character, even though in the regular expression used in programming, dot does have a special meaning. So let's do something unambiguous here and say, maybe give me something that uses what special characters we have in this definition. It is just the bar and the star and parentheses are special. The rest are assumed to be normal characters. Two bars next to each other should be illegal, right? Maybe A separated by two bars or star A would all be illegal characters, okay? So hopefully this is clear. Now we use this notation to describe grammars. Again, it's something that you have seen, but it's good to give names to the notation. So what are the red things? The red things are the characters that you can actually see on the input in those strings. These are called terminals because the grammar is used to derive the string, and you derive it using what are called non-terminals. These are just symbols that you need to rewrite all the way down to terminals. Non-terminals cannot appear on the input. They need to be rewritten to terminals, and terminals are characters because that's where the rewriting the derivation terminates. So terminals are the characters. Non-terminals are things that are recursively defined. There is a star non-terminal, which is the one that is mentioned here on the left. It's the one from where we start deriving the strings. And productions are 5 in this grammar. 1, 2, 3, 4, and 5. We list them more compactly this way. Okay? You may notice something interesting in the grammar, and that there are 2 vertical bars, a red one and a blue one. Are they really the same bars? Right. One of them refers to the input character, and the other one is essentially a special character for the grammar. It separates the productions from each other. So how would we typically distinguish between them? Usually our editor does not have colors like my PowerPoint does. We would escape them, and perhaps we would use quotes around here or backslashes, whatever the particular tool escapes. But now you could understand that even though the grammar is just a bunch of characters, some of them refer to special symbols in the grammar, like this bar or this, and some of them really refer to input, to terminals. Okay? questions about this as we go on, okay? Can you show a grammar for a grammar? You could show a grammar for a grammar. Grammar is what? Grammar is a sequence. Grammar of a grammar would be what? It starts with a non-terminal, so something like ID, okay? Then it has what? This symbol, right? Then it has perhaps IDs intermixed with special characters. Let's see if I can do this concisely. Maybe you say it's an ID or, let's say, character, and you need to have one or more of them. Actually, I erased too much. But yes, so ID, so this one here is this, okay? We'll put this in quotes to denote this itself. And now we can mix, say, ID and characters. So this would be the non-terminals, characters, one or more of them. And then the whole thing can repeat, can have 0 or more of them because you have multiple such productions. This is not quite complete. It doesn't allow these shortened productions here, but you get the idea. Okay, so here are the grammars. It's a grammar, not a grammar. Not that I really care, but it's sort of fun to realize that not all writing is due to bad grammar, which is probably what people tell you. So this mistake itself is not a grammatic mistake. It's a lexical mistake. It's a mistake that happens sort of in the word. You could say in the terminal rather than in how terminals are put together. So if this was a programming language, this mistake is a lexical mistake, a mistake found in the lexer, in the very front of the compilation or interpretation, not in the parser. And you should start learning where mistakes in programs are found by the compiler and interpreter. So this one here is a lexical mistake. So grammars and languages. I want you to tell me a grammar for this language of 1B followed by one or more A's. So this is a language that contains this string and then that one and that one and so on. Write down a grammar and tell me. I want to see whether we end up with just one grammar. Okay. It does not contain an empty string, right? So it contains exactly all strings of the form B and then followed by one or more A's. So that is an exercise that is in fact too simple for an exam, so you should be able to do this quickly. Clearly the definition will be recursive because we need infinitely many strings, and the only way to define them would be through recursion. Oh, it's much better. Look at this. Okay, so somebody wants to suggest the grammar? Yes. Let's do S, since it's usually the symbol. I used R only because it was the grammar for regular expression. So S. Okay, so okay, do we need, so this is, that's not what you said. You need to speak a bit louder. Uh-huh. Okay, that should work. One more. So does this generate the right string? Well, the base case is, okay. How about this? Now what we can generate is BA, right? When we go directly to the base case, when we go through recursion, we first generate SA, and then the S is rewritten recursively into BA and A, and so we seem to be good, okay? An alternative grammar. Can somebody suggest another one? Okay. One that will differ in significant ways. Okay. Yes. So S would go to B and E would be sequence of 1A or that should work too, right? Okay. So what we see is that we have one language, one set of strings, and many different ways how to describe it. Do you see any differences in these two grammars? Clearly, we pick different names. In one case, we use just 2 productions, 1, and another one. Here, we used 3, 1, 2, and 3 productions. The productions are the rules from the left-hand side of the non-terminal to what it is rewritten to. But I wonder if we can spot some significant differences that might make a difference. Okay. Excellent. So the answer is that here the S is on the left. So S is the recursive symbol, and it is on the left of that right-hand side. And here E is on the right-hand side. Okay. So this grammar here, I'll erase it actually, and we can look at the one here and another one there. And there is a left recursive grammar, which is this one. It's left recursive because S is right here. And this one is right recursive because the recursive symbol A is on the very right of the rule. It may seem insignificant, but we'll see in a few slides that it makes tremendous difference in some parsers. Some parsers cannot handle left recursion because they would get into infinite recursion. Could you give me a recursive grammar that is neither left or right recursive? Well, so if I change this to that, that would make it left recursive, because now the non-terminal A is on the left. See, this one is not recursive, because this A just goes here, and there is no loop going back to itself. So, not entirely, okay. So, it's neither left or right. Okay, let's try, please. Oh, I see. This, we've seen it in lecture 2, I believe. This is empty string. Good question. So this is an empty string, okay? We could do BA plus, but if we do BA plus, that's really just an acronym, a shortcut for saying, so BA plus is essentially something like S goes to B, A, and A is either 1A or AA. Right? So if you expand the plus, you end up with a recursion also. And you could write it as a left recursion or right recursion. So to let me tell you what it means to be neither left nor right recursive. It means that the symbol cannot be all the way on the left or all the way on the right. There must be some terminals in front of it. Okay, so how about if we do A is, right? It has now two A's, one on each side. So it generates an even number of A's. And we could use it to, of course, define even our language. All we need to say is, well, let me call this A prime to distinguish it, and it could be S is B A prime, okay, or BA, or this should be epsilon also. And yeah, I think that's it, right? So now it can generate both odd and even number of A's following B. And it is neither right or left recursive. Okay, so but let's start doing something more fun. So the parsers that cannot handle left recursion are quite common, so it's good to know what the left recursion means. And we'll soon see why that's the case. But we can rewrite the grammar to use a right recursion. For example, this you can rewrite into that. Okay, that's not surprising. This is what we've just done. The more interesting case is what you do with the grammar of expressions like this. This takes a while, so I don't expect you to come up with the answer right away, but maybe you have the idea of what we could do to remove the left recursion from such a grammar. You will see it many times in your project, so you will know what the answer is by the end of the semester, but can you get the key idea?
I guess we'd like to break it up into two, like E and some other one.
Okay, so we'll introduce a new non-terminal, exactly. We'll introduce a new non-terminal. So we have one non-terminal now, E. We'll have more. Okay, that's good. Okay, so what will we do with these more non-terminals? Okay. Okay, that would be one solution, that somehow the non-terminal will describe a part of the string. It will end with the operator. That's one solution, but we'll do something else, something more systematic than that. But that's a good solution that actually works. And try to see what we do with this grammar here. Imagine that our string is just A. How do we obtain such a string, A? Okay. Well, we'll start from E, derive E to T. You'll write it like this. Then T derives into F. Then F derives into A. So this is how we get A from the start non-terminal E. Now, what if we have a plus? What if we want to derive A plus A? Well, we do what? We do E goes to T plus E. What would be our next step in the derivation? We replace what with what? We would replace E with T. Okay, so we'll obtain T plus T. We have rewritten this into that. Okay. What would be the next step? Both of the T's will go to F's, all right? And now both of these can go to A's. Okay. Now we'll talk more about this on Tuesday, but if you see, we have introduced terminals, non-terminals T and F, which actually stand for something. T is a term and F is a factor. And they correspond to different level of precedence. Right? You know that multiplication needs to be lower in the tree so that it is performed before plus. And this grammar actually enforces this precedence. So that's all you need to understand now. But the key point is that it is not left recursive. At whatever symbol you look at here, say E, it is right recursion. Similarly for T, and similarly for this E here. Okay? So this is now not the left recursive grammar, and it is friendly to parsers. Okay, so now let's start designing some algorithms. So we do have a grammar, and we want to generate L of G, which is the language of the grammar, the set of strings that the grammar can generate. So could we come up with an algorithm that generates all those strings? If the grammar is infinite, then, well, you may not be willing to wait so long to generate all the strings, but imagine that if it is finite, we should eventually be able to generate them. So how would you write a generator of strings from the grammar? You may wonder why I'm asking. I'm asking because if we could write a generator, we'll just flip it around just so and obtain a parser. So let's start with the generator, because hopefully you will find a way how to, in a really dumb way, generate all strings from the grammar. So what would be a brute force way? It's, by the way, a common problem. Imagine you need to do testing of a sophisticated piece of software. Where do you get the tests? It would be nice to generate the tests automatically. If you could describe with the grammar the set of inputs that the program accepts and should handle correctly, you can then generate those inputs automatically, randomly. So that's a pretty common technique in testing, extremely useful. Well, so how do we generate them?
So basically, you take each known terminal and then replace it with each possible thing it corresponds to, and then just recurse until you get all terminal characters.
Exactly. So the derivation that we have done here on the right by hand, here we had in mind what we wanted to derive, right? But if we could just go left to right and take the start known terminal and replace it with one of its productions randomly, and then look at what we have here. Oh, here we have T plus E. We could pick T or E and replace it randomly with something, right? That's what you have in mind. And that will work. So here is the algorithm. I'm using this grammar for compactness. So it is left recursive, but it doesn't really matter here. And here is our generator. Okay? We call this function. It calls this E. And at the end, it prints end of file. We'll see soon why we need that. And here it makes a choice. And it chooses 1, 2, or 3. And depending on that, it prints A. Or recursively prints E, a plus, and another E. Or 3 does E times E. You see the correspondence between the generator and the grammar? There is one function here for each known terminal. This one for E. The number of cases is the number of productions you have, 1, 2, and 3. And the non-terminal calls itself because, well, it is recursive. So that's it. So do we believe that it will generate eventually all strings, or that for any strings from the language of the grammar, this program has a non-zero probability of printing it? It doesn't iterate through all of them, but every string has a likelihood of being printed, a non-zero likelihood of being printed. Okay, so that's fine. So we have a generator. How can we now, well, before we go to turning it into a parser, what is really important? Often in the parser, we don't just want to determine whether that string is a legal string or not, whether it has a syntactic error or not. What is actually more important is to obtain a tree that describes the input, right? And that thing is called a parse tree. The parse tree is nothing else, just a tree representation of the derivations that we have done. Right? So look here. If you look at one possible execution of that random generator, which we have just written, we start here, and now the coin or the random generator have flipped the coin and produce 2. So we generate now the second production, this one here, right? Because we got the random number 2. And we visualize it as so, right? Now it has 3 children. You generate E recursively, and another E, and a plus. Then in here we generated the random number 1. Here we generated 3, so there is another E times E. And here we generated 1 and 1. You see it here. So you see that the parse tree describes how that string was derived. In our case, it describes the random choices of productions. So here we have a production. Here we have non-terminal E, and we chose this production, which has number 2. We usually don't care what the tree is when we just want to randomly generate those strings. But when you are parsing, when you are turning the string, which is the sequence of leaves, when you are parsing that thing, you really need that parse tree, because that parse tree discovers the structure of that input. Right? In the case of the if then else, when we wanted to associate the else to the appropriate if, it would be the parse tree which would reveal to you how that else is associated, one if or the other. So how does the parse tree differ from the abstract syntax tree with which you have worked already quite a bit? Right, so in the parse tree, you really, everything you see on the input is in the leaves, and the internal nodes are the non-terminals, right? You can read out the grammar, in fact, from the parse tree, because every child, every node relationship with the children corresponds with a production. So when you look at the parse tree and you look at this parent here and these children here, what do? They correspond to a production, right? What production? E goes to E plus E. You can read out the grammar from the parse tree. That's too much detail, more detail than you want. So we abstract away the grammar detail and build ASTs on which the compilation, interpretation, program analysis can be done much better. Okay? So now we want to turn our generator into a parser. And we want to do it mechanically, meaning without thinking too much. Ideally automatically, but without thinking too much, we'll do. So how would we do it? Here is again the generator. Can someone suggest how we would turn it into a parser? Okay. Instead of print, we'll do a read. We could call it a scan, because scan usually means that you look at the next position of the input. If it matches what you expect, you consume it. If it not, then you say, I don't have on the input what I expect. Let me try another branch. Okay. So we'll replace print with a scan. Okay. So scan will look at the input. It will expect that character. If it's there, it will consume it. So what about the choice? What will that choice do? Are we still going to rely on a random number generator? I guess in principle we could, right? We could just run it, and instead of printing, we could read it. And after some time, the random number will give us the sequence of productions that parse the input. And that would sort of work, except it would take forever. And if there is a syntactic error in the program, it would just never terminate, right? Because you wouldn't know whether you're just making a bad random choices or whether there is a syntactic error in the input. So what do we do with that choice for the purpose of reading in the input and parsing? Okay. We could iterate through every choice, and eventually we sort of have to do it, but is there a mechanism that we are relying on in some of our projects that we could just deploy here? So think about a computer science major, right? You are not just going to iterate. You just sort of want to understand what's going on and say, I don't even need to implement it because I know there exists a way how to deal with it. You use some abstract magical construct. So what do we do for choice? You could use a dictionary, right? You could, but you're thinking sort of to implementation level. How did we, if you remember the sort of implementation steps we went to describe the Prolog interpreter, there was this easy step in the middle where somebody did a lot of work for us. So we could use coroutine to do that, but turns out parsing you can do with coroutines. But if I just want to explain the parsing to the algorithm, imagine you want to be on Who Wants to Be a Millionaire or What is the Show. At some point, you can pick up the phone and call somebody who will give you the answer, right? So could we do a similar trick here? We will just call the oracle, okay? And yes, the oracle can be implemented by iterating over all choices with coroutine, but I want to teach you how to think at a higher level and sort of decouple your thinking from, oh, I can iterate, or there is a coroutine. Once you start doing that, the thinking is too messy. And instead, you can say, I will use this non-deterministic parser, sort of relying on this entity, which at each step will make just the right choice. The choice is clairvoyant. It sort of predicts what other choices you have to make in the future when you ask for next choice. So exactly, we are just going to consult an oracle here. So here is the printer, the generator, and here is the parser. And here is also the scan. So if the input, the current input starts with S, then you consume S, else abort, right? If the input is syntactically correct, then there is no way how we'll abort because the oracle is going to give us a sequence of appropriate choices. Those that guarantee to make the right production so that you consume every character and at the end you can consume the end of file. Right? It's extremely a valuable concept to think of this non-determinism because you now understand parsing without having to think about iteration, coroutines, and in fact, how we make that choice now can be done in many different ways, but we can talk about it in the second half of the lecture rather than right away. Okay? So the concept of non-determinism, just asking the oracle for a choice, is one of the best inventions of computer science. We talked about the parse tree, but let's talk about it some more so that you understand why we actually parse better. We can walk through the parse tree and obtain the AST, essentially construct the tree, or you can directly evaluate the program if the program does not contain loops and it's enough, therefore, to walk over each node once. So here is a slide that shows how you could, given a parse tree shown on the right, you could actually evaluate the program. So again, the inputs are in the leaves. Here you see every production, right? Every edge is one production. So the three edges here are also one production. Which one? E goes to E plus T, right? And you just propagate these values up. And here when 4 meets with 5, you perform an addition. You obtain 9. And on the root, you get the value of the expression. It's pretty much like on the AST, except the tree has many more nodes, some superfluous when it comes to the AST. Right. All right. And you can go directly to the parser, as described, and make it generate the parse tree. So look what we've done. We still have sort of the parse routine, which calls the start non-terminal, and then at the end it expects to have read the entire input. Here is the procedure for E. We ask an oracle which choice to make. It reads A, returns A, and then it sort of parses the left-hand side, the right-hand side. It expects plus. and it returns this node of the AST. So what we are doing when you run into A, you return an A leaf. When you run into plus, you return a plus, and then another A. Here you construct here you construct this node, and so on. So the structure is before, except we are now returning the parse tree to the result. Okay. So how could we now? Okay, now we need to get to the business of implementing the oracle. Of course, we don't quite have the oracle. You could perhaps crowdsource the business of oracle to the net and just sort of pose the input string, outsource it on mechanical Turk, and say, well, tell me, guys, what decision I need to make here. And here it would not be a very fast parser, I suppose, also quite expensive. By the way, the parsers that we are running for you on the Google Cloud cost about $2-3 a day. I think that the crowdsourcing parser would cost more. So we really want to find a way how to run it efficiently without having to really ask people to act as oracles. So we could implement the oracle with coroutines through iteration, but we have already built the Prolog interpreter, which does essentially act as an oracle, right? It does the search. It finds the right match so that the goal can be proven to be true. So essentially, we already have built this power of the oracle into the Prolog interpreter. So we are not going to use for the lecture coroutines or anything. We're just going to write the parser in Prolog, and the Prolog interpreter will serve as our oracle. So let's go with this grammar. It is not left recursive because Prolog, even though it has an oracle itself, is not all powerful, and it would actually loop forever on a left recursive grammar. We'll see soon why. And we'll write it like that. So we'll have one predicate, E, and the way it will work that we'll pass the string here, and at the end of the parse, we expect an empty input. So you could think of it that this is the input string, and this is, sorry, I should say E, and this is the output. Or maybe I should call it the rest of the input. So here, this corresponds to the production E goes to A. So if I pass here a string, maybe A plus A, okay, what do I expect on the output from here? So if you remember, this is the Prolog notation for lists. This will separate the head from the rest of the list. And this out and that out are the same variable. So if I make a query E A plus A out, what will I get here? Assuming we only have this one single rule. You'll get plus A, exactly. So the output will be plus A. So if you see what's going on in this rule, this is one-to-one correspondence to what we had before in this non-deterministic parser where we had a scan. The scan checked for A. If it was A, it consumed it from the input and left the rest of the string untouched, the input string. So this rule here, okay, does nothing more than scan A. If there is A on the input, it will strip it off and return the rest of the input this way. Okay? So let me write here, this is a scan A. Okay? Now how about this production? How would you do that? Now we do need some recursion to implement that production. So again, keep in mind that we are doing nothing magical. We are taking our functional non-deterministic parser, which we understood a second ago, the one with the switch statement, and we are just turning it into Prolog so that Prolog does the oracular decisions for us. So anybody wants to write down what this rule would be? You could match multiple inputs. You could match, say, A and a plus. Absolutely, you could do that. Right? So you could match these two at once. Okay. And now you need something, right? So we actually need that exactly. Oops. Well, I think let's use what's here. Well, what are we doing? We are simply checking whether on the input we have A and plus. This is the rest of the input after A and plus have been stripped. This goes here, and now we are calling the parser recursively. It will parse whatever starts at R and return the rest in out, and this goes back here. Now, how do we call the parser? We just want to give it the input string, and we expect the whole thing to be consumed. So this here corresponds to scan end of file, right? The whole thing is consumed. We don't have a special marker for end of file, but we expect that the whole thing is consumed. So now in 3 lines, we had what we had before in more, and it does the entire parsing of this grammar. And I could run it for you, but if I just run it like this, it would tell me true. Okay? It is kind of beautiful that the power to make non-deterministic choices is to a large extent hidden in Prolog, and you can nicely exploit it. So let's look at, we just talked about how this works. So this is written here for you at home to read. Now, here is the parser for the entire grammar. Remember how we took the grammar of E plus E, E times E, and rewritten it to refer to terms and factors. Okay. So here is the entire Prolog parser for that. Again, here is the F part here, and here is this production, and here is that production. But again, the entire parser is right there. Now, could we extend this parser to also build the parse tree? Remember, we did that procedurally. Can we do it now in Prolog so that the result is a parse tree? So currently, the rules get the input. They will consume something from the input and return the rest. Now we want them to return exactly the subtree, just like before. And the way we do it in Prolog is, let's look at the base case, right? When you find an A on the input, you just return the A. This will become the leaf of the parse tree. Now, if you do the production, say the star production here, okay, you get the subtree to the left of the star here. The subtree for the right of the star is here. What are you returning? You are returning a new node of the tree with this tree hanging here, this tree hanging here, and this is a new leaf. And indeed, if you run this parse, you will get that. Just a flat representation of the tree. Okay? Now, one more quick look for you. Have a look at the program and tell me what do we need to change to produce an AST rather than a parse tree. Is this a simple change that we could do? Remember, the AST somehow omits some of the nodes that are in the parse tree. Okay, is this a small change? Right. Now, if you look at this here, if you look at this production here, we do not want to have any node for that, and currently we actually do. Right? When we take this production, it happens in this line, we do create a new node and attach the subtree to it. So how do we turn it into AST? Essentially, see here, whatever tree I get here, I just propagate. And again, tree that I get here, I just propagate. And for the star rule, I create a times node. There should be a comma. And this should be something like a plus. I'll need to fix these mistakes. So this should be a plus. And this is OK, but this needs a comma. And here, indeed, if you run it, you get an AST for that input string. Well, what do you think is the time complexity of such a parser? Given a string of length n, how fast does it run? So I have written it using the AMP language from 61A, or alternatively in Prolog. Here we are asking an explicit oracle here. Prolog is going to make these choices for us, 1, 2, 3. And in the worst case, each part of the input, it needs to make a decision. Am I going to go here or here or here? And of course, it cannot really make oracular decisions. It needs to try them, and then when it gets stuck, it will backtrack and try the next choice. So it turns out that the complexity is exponential because you need to make one of 3 decisions and then another one of 3 decisions, another 3 of decisions. So the parsers could run in exponential time. You could fiddle with the grammar to make it fast, but it could be, in the worst case, exponential, which is not that great. So I'll show you how to do it in a polynomial way, but let me say that this parser here that we saw is called the recursive descent parser. If you remember the calculator that we looked at in the second project, that is written as a recursive descent parser, not in Prolog, by hand in Python. And you should look at the code because it works exactly as the Prolog parser we have here, but written in Python. Why do you want to know that? Because each time you have a small parsing tasks, a small configuration file that needs to be parsed, this recursive descent parser is the way to go. It's an easier way to implement small, compact parser. In fact, languages like JavaScript in the Firefox browser have lexers, parsers indeed, which use exactly the same recursive descent algorithm. And they are fast enough. And they achieve speed by making it very easy to decide between the alternatives. They rewrite the grammar such that each time you need to make a choice, you can just look at the next symbol and say, oh, I know which way to go. So you don't need to try something and then backtrack and try another one. But let's see whether we can do this parser more efficiently than exponential time. We'll do it in polynomial time. And we'll develop what is called CYK parser. Does anybody know why the parser is called CYK? It's sort of named by 3 different people who invented the parser independently. So it's sort of the easiest systematic parser that you can build. It's so simple that you could invent it yourself. And in fact, with a little bit of guidance in previous years, we could just invent it during the lecture. We are going to do something cooler today. Rather than just inventing it, we are going to show you how, if you write it in Prolog just the right way, we can get this polynomial time parser for free. So what we'll do, there is a thing called Datalog. Maybe you learned about it in the database class. It's a well-behaved subset of Prolog. So certain things you rule out. And then the Prolog language becomes smaller, not everything is allowed, it behaves better. For one thing, it behaves now all of a sudden like real logic. I don't know if you looked in the art of Prolog, why Prolog is a mess rather than real logic. It's an interesting discussion why the meaning of logical not in Prolog does not really mean not. You know, no not always means no, apparently. But in Datalog, it always does. And so what is Datalog? It's a Prolog where you disallow certain things. One of them is you cannot have these nested compound queries or rules. That's a little bit of a problem for us because we implement the lists essentially with these rules, right? Our cons is like this F1. So the cons is not allowed in Datalog. So lists are out. Okay. And then you only allow so-called range-restricted variables. So when you have a rule like AX, then this X must appear here so that you could compute the value of X on the left-hand side from the value on the right-hand side. And then there are certain restrictions on how you use negation, but for us it's enough to say that let's just don't use negation. If we don't use negation, then we are definitely within the Datalog subset. And you can read more on this really well-written Wikipedia page. But why is it interesting for us? First of all, it has predictable semantics. Not all Prolog programs terminate. If you gave them a left recursive grammar, they would just keep expanding the goal, and they would recurse forever, right? If you give Prolog a rule like E in, and now you give it the same input, whatever goes here, so this is E, what would Prolog do? You call it on this goal, you match this goal, and now you recursively expand this goal. What would it do? It would just do it again and again and again until it runs out of stack. So that's a reason why the left recursive grammar does not work in Prolog, because the same value here, the same list, the same input is passed here without consuming a character. On a right recursive grammar, remember there is always some part of the input that you can scan, you can consume before you call yourself recursively, and so the input is shrinking, but not on the left recursive grammar. So with Datalog, all evaluations terminate, so there is no question whether the parser will get stuck. On every grammar, it will actually evaluate it. And then we don't need to do this backtracking business. We can nicely evaluate it bottom-up by essentially filling in a table, like in dynamic programming, and it will finish in polynomial time, in n cube. So, in fact, Datalog is so nice that we can use it to explain the parsing algorithms we will use in the rest of the semester. And we'll say, well, the CYK parser is really just the Datalog version of the Prolog recursive descent parser. So what we'll do, we'll take our parser here, massage it a little bit to be in the Datalog subset, and it will all of a sudden run not only in polynomial time, it will run for any grammars, left recursive too. And then the Earley parser is just some optimization on the CYK. I won't quite explain what the magic transformation is in general, but specifically you will see how you can make it much faster. But the bigger lesson for CS164 is that if you take a language and you throw out features from it and you say you can only do this, but not that, all of a sudden the language is easier to understand, implement. Imagine scheme from which I remove recursion. It would be much easier to write an interpreter for it if there was no recursion. It's a different story that you couldn't write too many programs, but you would not need to have a stack for one thing, right? So the ability to subset the language to a smaller set of features is extremely powerful. So when anytime in doubt, throw it out. And the Datalog is a nice case because we are restricting it quite a bit, but it turns out to be enough for our parser. So let's see. So is our parser actually in, it is in Prolog clearly, I ran it this morning, but is it in Datalog? So does it have no negation? There is no negation in those rules, right? It's, by the way, the entire parser for this grammar. Is it range restricted? It is, because this out value is computed from the right-hand side. R is computed from here. So yes, we can compute the left-hand side values from the right-hand side, which is why you can compute it bottom-up from ground facts rather than backtracking top-down. So that's good. Does it have compound predicates? Yes. The lists here, this is essentially a cons, right? So we need to do something with those lists. So we cannot do it completely automatically. But if we have an idea how to rewrite this parser so that it doesn't use lists, we create ourselves a CYK parser. We can add your initials to the name. So how do we get rid of those lists? Any ideas? So you essentially want to break the list such that every element of the list is a separate parameter. But the list could be of arbitrary size. So I'm not sure we can do that transformation. So what if I give you the ability to sort of index into an input array? Imagine that I do give you that in Datalog. That's actually easy to do. That we read in an input, we put this input into a big predicate. Something, if we have an input A plus A plus A, then maybe we could have a predicate called input 0 is A, input 1 is a plus, 2 is an A, 3 is a plus. Would that be, that allows us to access all characters of the input, right, without having to use lists. Okay, so now we do have access to the input. Can we now, with this representation of the input, okay, so we do have one representation of the input, can we use that to rewrite our parser so that it is in the Datalog subset? And remember, the only thing we need to do is get rid of those lists. Okay, so I think we are on the right path. So instead of out, we are storing the number that is the rest of the input. That turned out is not quite yet. Well, it could be maybe enough for that. Yeah, maybe yes. So let me show you what the solution is. It is pretty much like you are describing. So we are now going to make the E predicate not to use string coming in and the rest of the string coming out. Predicate E will compute two indices. And they will be such that this Eij is true if this segment of the input from the I symbol to the J symbol can be derived from E. So if I have here an input, and here is I, and here is J, if this here is A plus A, okay, then Ei and J is true. Why? Because the segment of the input between I and J is derivable from E. Yeah? So now we are representing the input by saying, if this is I, this is J, anywhere in the input, if I can derive this segment here from E, then Eij is true. Clearly, if this here is a plus, then is it the case that Eij plus 1, is Eij plus 1 true? When what follows it is a plus. Can I derive A plus from E? It's not a string derivable from E. It's not an expression, right? There is this hanging plus. So this would be a false. Okay? Now let's look at the algorithm. The first rule, again, how many rules are we going to have? Again, like 2 again. right? This is the base case. What does it say? That this is true when what? When on the ith position of the input we have an A. This corresponds to this production, right? So does that correctly implement the production? If you find a chunk of the input, just one character that is an A, is that A also an E? It is derivable from E, okay? I have a few alternative ways to explain it. Now let's look at this production. So now I call it with I and j that could be arbitrarily far from each other, not just next to each other. So I and j. And let's see. We are asking now, does there exist some k such that this part of the string is derivable from E, I to k minus 1. The kth one is a plus. And then the rest from k plus 1 to j is derivable from E. Essentially, what we are asking here is that if this is I and this is j, we are looking for something derivable from E here. Then we are looking for a plus here and another thing derivable from E. And this here is the kth index. So this part here is E, and this is E. Okay? And similarly for the star. Now, I have two ways how to explain what's going on here. The first one is, how would we evaluate the program? Can we go bottom up and start from the simplest facts and then build more? So if I give you an input, let's now, I'll write this down by hand later. And if I do this, so this is 0, 1, 2, 3, and 4. And let's make it A plus A plus A. Okay. If you look at just this rule, what facts hold true right away, given this input? Imagine we want to do an iterative algorithm. We see which facts hold right away, and then given those, we deduce more facts and more facts and more facts. Okay. I'm going to represent them just a second this way. Are you asking about the first rule here? Yeah, let's assume that the input is broken into single characters. So every element of the input contains just one character. Was that the question? No, as think of this one, okay, a good question. So imagine this is I here, and this is I plus 1. Okay. So this rule here is really asking about this element here. So I plus 1 is indexing to the next one.
So if you just from the fact that you have I k minus 1 in the lower two rules, so it should be E of I k.
It will be, yes, it should be. And indeed, I had it correct this morning, and I screwed it up thinking that I did the right thing. Okay. So this is the one algorithm I did not run. All right, good. Excellent. So which facts hold right away? Can we put into this table information about which facts hold given this first rule? So let's say this is I, and here is J. So 0, 1 holds, okay. 2, 3. Okay. Okay, so these indeed hold, right? That's what we know given the first rule. How about now, given this knowledge, can we use this rule to learn some more? So essentially, what do we know? We know that this is an E. We know that this is an E, and this is an E. This is what we have learned in the first round, right? We know that this can be derived from E, and this and that. Can we now learn that this whole thing here is an E? Right? We should be able to see that this is an E, then there is a K, which is a plus, and then that one. Okay. So we do have 0, 1, which is here. Now, do we have a plus in number 1 position? Yes, it is here, right? Here is that plus. Oops. And then we have 2, 3, which is here. And therefore, this here is an E as well. By similar reasoning, we can show this one, right? Or did I miss it by a point? 0, 3. It should be 0. Yes, it should be 0, 3. Okay. Yeah, absolutely. And it should. And then the E that corresponds to this one here would be 2, 5, right? Would be 2, 5. And in the next round, we take the information about these two and we put them together. And this is the knowledge that the whole thing here can be derived from E. Now, this is all written here, so you can step it up by hand again. But this is a more interesting way to think about it. And indeed, this is why it is on the T-shirt, because you will see this algorithm again and again when you work on Project 4. And this will make it really clear, this graph representation. So when I take an input, I can represent it as a graph. What kind of graph? A chain graph. One edge for each element of the input, right? And now I'm going to go bottom up and perform what is called a reduction. So when I see an A, I see, oh, I see there is a production that goes from E to A. So I can take this A, which is the right-hand side of this, and reduce it to its left-hand side. So I can now place an E here, and another E, and another E. Okay. Then what other E's can I place? Now we see what? We see E plus E. Is that also an E? Yes, because we do have another production which says E is E plus E. And we see the right-hand side right here. Right? We see this E here and a plus and E next to each other, which means that the whole thing from here to here is derivable from E. We are reducing this right-hand side to the left-hand side. And we do the same here. And now we see what? You see one E here and a times an E. That means that the whole thing is derivable from E. or with animation, you do this in the first step. Then once you have these two E's, you can do that. Then you can do this. And the fact that we have placed an edge, that we managed to place an edge from the beginning to the end, is labeled with the start non-terminal, signifies what? It signifies that we can derive the entire input from the start non-terminal of the grammar, but we built it how? We built it bottom-up by looking at the individual characters and reducing them to the left-hand side of the non-terminal until we were done. So I'll leave you with that. You can look at the slides and see how, given this graph, what we could call CYK graph, you could reconstruct the parse tree. Can you look at the graph and see the parse tree in it? Right? Sort of, there is a mix-up between nodes and edges, so it's interesting. But yes, the parse tree could be read out from here. And we'll continue on Tuesday. I'll tell you about the Earley algorithm, and then on Tuesday, you'll get a homework in which we'll give you an Earley algorithm running, but extremely inefficient. It will run like n to the 4th. It will probably parse 20 characters. And you'll have to optimize it to get it down into linear time so that you can actually use it as a parser in your project. Essentially, it will be an exercise in designing good data structures. OK, thank you. I don't think either of them has office hours after class. But tomorrow you can pick them up. OK, so today I just want to say that we are going to give extra credit for any bugs that you find in the handout, solutions, starter kits, and we'll keep track of it on Piazza. Today, you know, Thursday is no laptop days, and that's good because there is a lot of material that we want to cover that you may want to think about every slide that we'll go about. So parsing, why do we care about parsing? We want to make sense out of these sentences. A sentence like this one. You see a problem that shows up in parsing of the sentence? So depending on whether there is a serial comma or not, depending on whether you put a comma or not, the association of Mother Teresa and Pope could be, well, they could be my parents. That was the meaning as written because there was no comma. Or they could be the people to whom this lecture is dedicated. And you can guess the meaning from the context, but without the comma, indeed, the meaning was that they are my parents. OK, I want to start with a better answer to a request. I don't think I justify the answer quite well. So the request was for solutions for PAT to provide binaries rather than just the handout. Well, I'd love to do it, but I cannot do it for two reasons. One of them is that there are no such thing as a binaries for Python because there is bytecode, but you can reverse engineer it in a few minutes. So that would leak the solution out. And the project took quite a while to prepare, and we cannot change it every year, so it must not leak out. Hence, you are getting only hard copies. And there is an educational benefit to getting just the hard copy, and it is that you actually need to read what the solution is. Well, you could just retype it, but I don't think it will work that way. So that's how it is. I'm sorry. Yes? You could, but then you couldn't test it on your own machine, right? Because you would need to always go through the autograder. The binaries would need to reside on the server, so you would need to somehow check in. It would need to be shipped to the server. And so that's something I will insist on. I'm sorry. If you did not finish the assignment, we expect you at the very least to understand. So regular expressions are described with a grammar that is inductive. Recursive, almost like any other grammar. And what it says that there is a base case, and any character C is a regular expression. So A is a regular expression, and so is B, and so is C, and so on. And then the inductive case, if we find regular expressions E1 and E2, then the alternation, the concatenation, clean closure, and the regular expression in parentheses, these are regular expressions as well. So the grammar therefore describes which strings are sort of legal strings, legal program strings that we want, and indirectly describes which are not. Okay? So give me a few examples from the language. Just one quick example that is derivable with this grammar. A will work. Okay. One more. Okay, so we'll do this. This is from the language, clearly. Give me a few that are not from this language. So A dot, well, now it really depends whether dot has a special meaning or not. According to our description, the dot would be probably just a character, even though in the regular expression used in programming, dot does have a special meaning. So let's do something unambiguous here and say, find what the right solution is and fix the few bugs by taking the hard copy of the solution and putting them in.
Can we find out what test cases we missed on PA1?
Test cases on PA1, we are going to release, push into your repositories the test cases. Not all of them, but I think the strategy that we'll use that we'll push back 5 test cases for everybody based on which are the most frequent ones that people failed. So if you failed 10 test cases, you'll get 5 back, those that caused most problems for everybody.
So if we type in the handed answer, these are not going to work right out of the box. Is that what you're saying?
I think they should. Yeah. Well, I don't know now. Okay. That was probably a problem. The question was, what do we do? Can you ask for a resubmit after you picked up the I see. Oh, you still can pick them up, right? Absolutely. So you can just come to the office hours tomorrow and pick them up. Yeah, there is a stag on Sean's and Thibault's desk, and you can pick them up. Excuse me? I don't know if they are going to be there. Probably not. And the second one is here, and again there is an error. There is a hyphen which changes the meaning to, instead of 7 doctors, these are doctors who are 7 feet tall or wide, or I don't know. That's one of the two. And then a meaning of this, which is more relevant to the class. Can you see what the ambiguity might be here?
Like the order of the evaluation problem? Is it if E1, then the rest of everything? Or if E2, then the rest of everything, and that's the else stuff for E1?
Right. So to put it more concisely, the answer is good. But to say we are really asking, is this else associated with this if or with that if, right? It could be one or the other. And so in general, parsing is the process of taking text and turning it into some sort of structure, usually a tree that shows how things are associated, how they are evaluated. It's true for natural language. It's true for computer programs. And there is a lot of text out there. Just think of HTML, JSON, and all the things that you will need to parse, in addition to programs. So grammars are the things that describe strings. Essentially, a grammar is what the description of a set of strings. That set of strings that the grammar describes is a language. And we have seen it before. But let's recap it on the case of regular expressions.